In today's class, we are going to prove how we can prove an irrational number as irrational. So, let's take the first example. Prove that root 2 is irrational. To solve this question, we use a method called the method of contradiction. So let, if possible, root 2 be rational. We'll assume the contrary. Therefore, there exists. So since root 2 is rational, we can show it in the form of p by q. So therefore, there exist p and q co-prime to each other such that root 2 is equals to p by q, where p comma q belongs to integer and q should not be equals to 0. This is our standard rational number, how we represent a rational number. We take in the form of p by q, where p and q are integers and the denominator should not be equals to 0. Okay, now what does p and q co-prime to each other mean? Suppose we take the number 5 by 25. So 5 by 25 is 1 by 5. So what we are doing is, when we are taking this p by q, this is also rational, but we are not taking in this format. We are taking in this format, means the numerator and the denominator does not have any common factor. Co-prime means there should not be any common factor. Like 2 by 3 is co-prime. There is no common factor between the numerator and the denominator. This is what co-prime means. So we are assuming that p and q are co-prime to each other. Next, which implies, so root 2 is equals to p by q. So q root 2 is equals to p, squaring both sides, q square is equals to p square. So this implies p square is a multiple of 2. So p square is a multiple of 2. And if p square is a multiple of 2, so this will imply that p is also a multiple of 2. Because the square of any number, if it is a multiple of 2, the number itself is also a multiple of 2. Now, since p is a multiple of 2, we can take p equals to 2r. So, squaring both sides, p square is equals to 4r square. So this implies, see, in equation 1 we have p square is equals to 2q square. So instead of p square we can replace 2q square is equals to 4r square using equation 1. So this implies q square is equals to 2r square. 2 and 4 cancel off, only 2 will be left. So this implies q square is a multiple of 2. Then if a square of a number is a multiple of a particular prime number, then q is also a multiple of 2. Hence, P and Q have a common multiple two, but this contradicts our assumption that P and Q are co-prime. We assume that P and Q are co-prime, means they should not have any common factor. But P and Q, according to this theorem, we are getting P and Q are having is a common multiple 2. So this becomes a contradiction. Therefore, we conclude that root 2 is irrational. Therefore, root 2 is irrational, as the contradiction has arisen from our wrong assumption that root 2 is rational. Since our assumption was wrong, that is why this contradiction has arisen. Hence, root 2 should be irrational. This is a standard procedure that you need to follow to prove that root 2 is irrational. Okay. Example 2. In the same way, you can show root 5 or root 7 or root, say, 11, any number as a rational number. So, example 2. Show that 5 minus root 3 is irrational. If you have to show root 2 or root 3 or root 7, root under of any prime number, you need to follow this particular steps. But when you are given 5 minus root 3, we need to show that this is irrational. We will follow a little different method. We'll follow the method of contradiction itself, but the procedure will be a little different. So let, if possible, 5 minus root 3 be rational. We are using the same language. Let, if possible, root 2 be rational. Here we are taking, let, if possible, 5 minus root 3 be rational. Therefore, there exists co-prime P and Q such that 5 minus root 3 is equals to P by Q, where P comma Q belongs to integer and Q is not equals to 0. From here, what we get is, this implies 5 minus P by Q comes to the left hand side, minus P by Q is equals to root 3. So this implies root 3 is equals to 5 minus p by q. Now, since p comma q are integers and q naught equals to 0, and so 5 minus p by q, so these are two rational numbers. Subtraction of two rational numbers will get a rational number, and so 5 minus p by q belongs to the set of rational numbers. So if the right hand side is a rational number, the left hand side also becomes a rational number. So this implies root 3 belongs to the set of q. But we know that root 3 is irrational. But this contradicts the fact that root 3 is irrational. So we conclude that 5 minus root 3 is irrational, and the contradiction has arisen due to our wrong assumption. So this is how we'll solve this type of questions. The third example and the final example show that 3 root 2 is irrational. This also will solve it in quite a similar way. See, like in the first sentence, what we'll do is we'll assume that it is rational. So let, if possible, 3 root 2 be rational. Then in the next statement, what we will do is we'll take two coprime numbers p and q such that the number will be equals to p by q. So therefore, as this is rational, there exists coprime p and q such that 3 root 2 is equals to p by q, where pq belongs to integers and the denominator q should not be equals to 0. So this implies root 2 is equals to p by 3q. Now, since q not equals to 0, therefore 3q is not equals to 0, and p comma 3q belongs to integers. The denominator is not 0 and the numerator was an integer, and 3q, as q is not equals to 0, 3 is an integer, q is an integer, multiplication of two integers will get an integer. Now since the denominator is not 0, therefore 3q is not equals to 0 and p comma 3q are integers, therefore p by 3q belongs to the set of rational numbers. which implies root 2 belongs to the set of rational numbers. Quite like this only, but this contradicts the fact that root 2 is irrational and the contradiction has arisen due to our wrong assumption that 3 root 2 is rational. This was our initial assumption that 3 root 2 is rational, and this, since the contradiction has arisen, so we say that our assumption was wrong. So we conclude that 3 root 2 is irrational. Okay. So root under of a prime number is irrational. This is how we'll proceed with the proof. Subtraction or addition will proceed with the proof in this manner, and for multiplication will proceed in this manner. Multiplication or division will proceed in this manner. Okay. Last example, I'll show you how to prove that root under of any number that is not a perfect square, say root under of 6, is irrational. This proof will be very similar to the first proof that we did for how root 2 is irrational. Not exactly same, but quite similar. This is our example 4. So, solution. In the beginning, we'll take, let if possible, root 6 be rational. Therefore, there exists coprime P, Q such that root 6 is equals to P by Q, where PQ are integers and the denominator Q is not equals to 0. After this, what we are going to do is we'll square both sides just like we did in the first example, squaring both sides. What we get is 6 is equals to P square by Q square. So which implies 6Q square is equals to P square. Now 6 is a multiple of 2 as well as 3. It is your wish, you can take either 2 or you can take 3. You can take any one of them. Let's say I take 3. So this implies P square is a multiple of 3. You can also take another step and show that this is equals to 3 into 2Q square is equals to P square. If you would have taken for 2, you could have taken 2 outside the bracket and 3 inside the bracket. So P square is a multiple of 3. So this implies P is also a multiple of 3. If the square of a number is a multiple of a prime number, then the number itself is also a multiple of the prime number. Now, let as P is a multiple of 3, P is equals to 3R, where R belongs to integer. So, squaring both sides, we get p square is equals to 9r square, and p square was equals to 6q square. Let's mark this as 1. So this implies 6q square is equals to 9r square using 1. So this implies 2q square is equals to 3r square, or q square is equals to 3r square by 2. Now over here we can see q square is a multiple of 3, which implies q square is a multiple of 3. So q is also a multiple of 3. Therefore, just like we did in the first example, next we have shown that they have a common multiple 2. P had a multiple 2, Q had a multiple 2, hence P and Q have a common multiple 2. This contradicts our assumption that P and Q are co-prime. In the same manner, we will take, therefore, P and Q have a common multiple 3. But this contradicts our assumption that P and Q are co-prime, and the contradiction has arisen due to our wrong assumption that root 6 is rational. This is the wrong assumption. So we conclude that root 6 is irrational. This was our last example. Now we'll proceed on to the exercise as your assignment.